Okay, last big idea here. We're looking at Pascal's triangle and how it can help us with the binomial expansion. So I'm assuming you've seen Pascal's triangle before, but if not, here it is. The first row we actually call row 0. Okay, and that's important. Row 1 has 1, 1, and then to get the following row, to get the subsequent row, so we add 1 and we get 2. Okay, and then 1s are always along the 2 outside edges, right? And then we can get the following rows by doing that same pattern. So here we have 1 plus 2 gives us 3, and 2 plus 1 gives us 3. So our third row is 1, 3, 3, 1. Okay, and so on. And we can use those as coefficients in a binomial expansion. So binomial expansion, what we mean there, for example, when we raise a binomial, so 2 terms added or subtracted together, in this case A and B, when we square them, we always do FOIL, right? But what we're really doing is a binomial expansion. We're doing it to the power of 2. Okay, so notice that if we look at row 2, so 1, 2, 1, and here we're raising our binomial to the power of 2. Look at the coefficients when we actually expand it. We have 1a squared plus 2ab plus 1b squared. Okay, and that pattern is going to hold true for every row of Pascal's triangle and every power of the binomial expansion. So if we raise that same binomial to the power of 3, we're going to use these as our coefficients. We're going to use row 3 of Pascal's triangle, and notice it's 1, 3, 3, 1. 1, 3, 3, 1, just like row 3, right? And so on. We can do that forever. You know, infinitely if we like. But for our cases, we'll only use kind of the first couple rows. If you're looking for an extension of this, how you can get any row, because really, I mean, who's going to sit down and write out the, I don't know, 10th row of Pascal's triangle, or, you know, the 50th row or whatever. So there is another way to come up with these coefficients. But for our purposes, just for this class, we won't use that, but I'll show you an extension if you're interested. Okay, also you should notice, so not only are the coefficients those in Pascal's triangle, the third row, for a binomial expansion to the third power. What also happens is whatever a is, that's going to be raised to this same power. So it'll be cubed. And then it reduces in 1 power, but b gains a power. So really this is a cubed times b to the 0, which is 1. Right? Anything to the power of 0 is 1. So here we've got a coefficient of 3, we've got a squared, and then times b to the 1. And then in the next term, a reduces a power, so a is to the first power now, and b gains a power again, so b is squared. And in the last term, a is to the power of 0, which is just 1, which is why we don't write it, and b is cubed. Okay, so just remember, you're going to use that row of Pascal's triangle for your coefficients. And then a is going to start as the highest power, and b is going to start as the lowest power. And that power is going to be whatever your power is that you're raising your binomial to. So let's look at this. If we use the binomial expansion for a plus b, the quantity cubed. Okay, so remember we just looked at that, so that's 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. Okay, so those coefficients come from Pascal's triangle, and then we start with the highest power for a, and then we end with the highest power for b. So in each term, b gains a power and a loses a power. Okay, so we're going to use that model to expand this binomial. So if we didn't use that model, we would have to multiply this binomial by itself 3 times. So that's one way to do it. Square root of 3. But I think you'll find a bit faster and more versatile is to use the binomial expansion. So instead of a, we're going to have 2. Okay, this is our a. And instead of b, we're going to have the square root of 3. Okay, so we're going to have 1 a cubed, so 2 cubed, plus 3 a squared. B is the square root of 3. And that's to the power of 1 plus 3 times our a, which is 2, times our b, and we want to square that, plus 1, and then b cubed. Okay, and then of course we simplify this. So 2 cubed is 2 times 2 times 2. So 2 times 2 is 4, times 2 is 8. 1 times 8. Okay, then we've got 3 times 2 squared, or 3 times 4, and then the square root of 3. Okay, here we have 3 times 2, which is 6, and then the square root of 3 squared. Remember what happens when we square a square root? It just becomes the quantity that's under the radical. So the square root of 3 times itself gives us 3. Okay, the square root of 3 squared. So what's really going on is they're canceling each other out. Okay, then the square root of 3 cubed. So it's the square root of 3 times the square root of 3 times the square root of 3. Well, these we know are equal to 3, so we've got 3 square roots of 3. Okay, and finally we just simplify everything, so we've got 8 plus 6 times 3 is 18, plus 12 square roots of 3 plus 3 square roots of 3. Okay, so 8 plus 18, we've got 26, and 12 plus 3, 15 square roots of 3. Okay, and likewise we could do the same thing with this next example. Again, if you want to just pause the video, try it yourself, and then check your answer. Okay, so if you just want to check your answer. So for part B, you should have this. Just remember in the third step here, we can only combine like terms, right? We can only combine like surds. So we've got 5 square roots of 5 plus 6 square roots of 5, so that's 11 square roots of 5. Okay, we can't combine the square root of 2 and the square root of 5. So the 15 square roots of 2 and the 2 square roots of 2 give us 17 square roots of 2. Okay, so you can stop the video here if you feel like I've had enough today, I'm doing good, I feel challenged, I don't need to challenge myself anymore. If you still feel up for a challenge, you can continue watching. Back to Pascal's triangle. We can write Pascal's triangle using the binomial coefficient. Okay, this binomial coefficient, it just requires some use of factorials. So, for example, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. That's all factorial means. That's what that exclamation point is. 0 factorial, by the way, is 1, and so is 1 factorial. Okay, so we say this, we say n choose r when we're speaking. Okay, so that's called the binomial coefficient. Coefficient because it goes in front of the numbers of our binomial expansion. Okay, so n choose r. All of these are of the form n choose r. Okay, the number on top, we're going to do that factorial. And then the number below, we're going to do r factorial, so the number below. Times n minus r factorial. Okay, so some context. Let's use this one here. 4 choose 2. Okay, so what that means is do 4 factorial, so n, and then r factorial, and then n minus r factorial. Okay, so what that looks like is 4 times 3 times 2 times 1 on the top, over 2 times 1, and then 4 minus 2, of course, is 2. So again, it's 2 factorial. Okay, so we've got some canceling we can do, and we can start to cancel because everything is multiplication. or division. So we've got 2 times 2 in the denominator. Those can cancel with this 4. And so all we have left is 3 times 2, which is 6. So this binomial coefficient right here is equal to 6. And if you were to go back to the Pascal's triangle, you'd have 1, 3, 3, 1 right in the third row. And then you'd have 1. If we add 1 and 3, you get 4. If you add 3 and 3, you get 6. And if you add 3 and 1, 4 and 1. So yes, it is 6. Okay, why does this help us? Well, like I said before, you might not want to do Pascal's triangle you know, an infinite number of times. There might be times when you don't want to do Pascal's triangle to row 50. You can just use the binomial coefficient. So let's look at this. So all that's changing, okay, this is still always going to be 1. This is n choose 1. So it's n factorial over 1 factorial. And then this will be n minus 1 factorial. Okay? This will be n factorial over 2 factorial times n minus 2 factorial, etc. Okay, I'm not going to spend a lot of time with the calculations because I assume if you've gotten this far, you're interested and you're up for the challenge. So if we want to expand x plus 3, this binomial, to the power of 10, if we want to expand that, we're going to use 1, or a, sorry, which is actually x. A is x in this case, and b is 3. Okay, so we've got 1 times x to the 10th plus n. Okay, so n is 10. This is n. Okay, and we're looking at choose 1. So we've got 10 choose 1. We'll have a to the 9. We'll take 1 away from, sorry, x. We'll take 1 away from the power of x, and we'll add 1 to the power of 3. So 3 to the power of 1. So this will be 10 choose 2, x to the 8th. So we're taking 1 power away from x. We're adding a power to our 3. And notice that these powers, so the power of x and the power of 3 should always add to 10, because that's n. So it should always add to n. So 9 plus 1 gives us 10. 8 plus 2 gives us 10. 10 plus 0 gives us 10. Okay, this is 10 choose 3, x to the 7. Ten choose 4. Okay, and so on. I'm not going to keep wasting your time writing it all out. Okay, but what I do want to show you is the calculation of the binomial coefficient. So this is going to be 10 factorial over 1 factorial times 10 minus 1 factorial. Okay, so it's going to be 10 times 9 times 8 times 7 over 1 factorial is just 1. 10 minus 1 gives us 9. So 9 factorial. So it's 9, 8, 7, 6, 5, 4, 3, 2, 1. All of this is going to cancel, and it just gives us 10. So anything choose 1 is always going to be itself. So this is just going to be 10. Okay, 10 choose 2. Same idea. So you'll do 10. Okay, and that is over 2 factorial, so 2 times 1, and then times 8 factorial, right? 10 minus 2 is 8, so 8 times 7 times 6 times 5, 4, 3, 2, 1. Okay, so all of this cancels, and then we'll cancel a 2 from our 10, so we'll have 5 times 9, so this is 45. Okay, so if you were to do Pascal's triangle to the 10th level, you'd find the coefficients were 1, 10, 45, and so on. Okay, I'll leave that open for you to play with. Okay, great. So thanks a lot.